The Topographic and Extreme Atmospheric Environment Lander, or TEXAN lander for short, is a proposed mission by a team of students from the University of Texas at Austin in preparation for the NASA Glenn Research Center University Student Design Challenge and for the ASE 374L Space Systems Engineering Design course. The TEXAN lander mission was developed by undergraduate seniors Maxwell Carlile, Robby Keh, and Austin Uresti from the University of Texas at Austin Department of Aerospace Engineering. The team was supported by faculty supervisor Adam Noakes. The TEXAN lander is designed with the sole objective of surviving on the planet Venus, Earth's much harsher and more volatile sister planet, where temperatures average 864 degrees Fahrenheit and the atmosphere is composed of predominantly carbon dioxide with clouds of sulfuric acid. This environment typically renders most landing craft useless within a matter of hours. Per NASA Glenn Research Center directive requirements, the lander must land and successfully operate on the surface of Venus for the full mission duration of 90 Earth days. Additionally, the mass of the lander cannot exceed 1,500 kilograms, must have a scientific instrumentation allocation of 200 kilograms, be capable of atmospheric and surface science, and communicate with Earth through means of an orbiting relay. The primary consideration for the TEXAN lander's design is thermal insulation to survive the Venus environment. The lander consists of an aerogel and silicon nitrate thermal tile surround, a titanium composite outer housing, and an interior ceramic core electronics housing. This passive insulation combines with active cooling and power generation using a Stirling engine with exterior heat radiating fins. The lander launches aboard a United Launch Alliance Atlas V rocket, similar to its 2020 Martian counterpart, stored in the upper payload fairing attached to a Centaur upper stage. 3 minutes into launch, the Centaur upper stage propels the TEXAN lander and orbiter out of Earth's upper atmosphere to a Venus transfer trajectory, thus beginning the cruise stage. Once the spacecraft has begun its cruise to Venus, the gimbaled solar panels and the secondary omnidirectional antenna are deployed. For the duration of the cruise stage, the spacecraft performs trajectory analysis, navigational corrections, and vital system checks, reporting back to mission control periodically. After a 128-day cruise stage, the orbiter and lander perform final system checks and trajectory corrections before beginning the entry, descent, and landing stage. During EDL, the lander is released from the spacecraft to begin its descent orbit insertion to the surface, and the relay then begins its parking orbit around Venus. During descent, a parachute is utilized to decrease the descent velocity through the upper atmosphere. Shortly after the parachute is deployed and the descent velocity has slowed, the lower heat shield is jettisoned and lofted environmental and atmospheric Venus Sensors secondary payload, or LEAVES for short, are propelled into the atmosphere using a chute and roller system mounted to the bottom of the descent vehicle. Once deployed, the LEAVES begin data collection on the atmospheric conditions at various altitudes and transmit the data to the orbiting relay above using a small onboard sensor suite. The LEAVES container and launcher is then jettisoned, allowing for the final descent of the lander. Once near the surface, the lander is released from the upper heat shield and parachute, free-falling for the final 50 meters. Upon landing, the lander performs system checks, deploys the antenna, and then begins its scientific operations, ready to study Venus more in depth than any mission before.